Hello and welcome to another episode of How to Understand X, this time being a mini episode in which we target something that you already probably have a good understanding of, and that being Heron's formula. If you're wondering why we've gone from derivatives to elementary trigonometry, I can't give you a very good reason for that. Uh, I suppose I could tell you my general upload schedule, or at least the way I want to structure my future videos. I want to do like a 4 or 5 part mini series on, calculus with some supplementary material like worked examples or, just further exploration of some topics. And that will be the 4 videos. One's already done. That would be derivatives, integrals, limits, applications of the derivative slash integral, and then probably series, even though that doesn't fit within the AP Calc AB curriculum. I think that will allow like someone who has already taken the class or has already done a good amount of it, if they watch those videos, I think they'll have a pretty good understanding of what they've been doing. And in between those pretty large videos, I'm going to be doing, stuff like this, where we talk about things that you probably already know at least a good amount about, but you might want a more in-depth analysis of these smaller topics. And, in between those calculus videos, I do want to talk about other stuff. I was thinking about doing a video on writing mechanics, sentence structure, and figures of speech, or even like just a catch-all video of how to write essays better. Um, I'll actually spoil the premise of that video and just kind of just say it right now. If you want to write a good essay, just vary your sentence structure. You will not imagine how many essays that I've written and read that all sound and look the exact same. Well, not sound the same, but read the exact same. Because, we just have this very, needlessly academic way of writing that doesn't allow for varied sentence structure. And varied sentence structure is kind of the basis for any interesting essay. But I'll talk about that later. And yeah, that'll be my general upload schedule for the foreseeable future. I might do some videos on, engineering principles like fluid mechanics or like load bearing, stress calculations, just anything that pops in my head. But yeah, today though, because we're not doing all that right now, we're going to talk about Heron's formula. You might have seen this at some point. It's just the way of defining the area of a triangle. If you know the sides, it is the area of the square root. I mean, not the area of the square root. The area is the square root of s times s minus a times s minus b times s minus c. And I'll extend that and then draw that a little bit better. Not particularly better. Let me actually try and make an actually good C. It'll be like that. So, S in this context means the semi-perimeter, or if we know our stems, semi is half, we will have A plus B plus C. If we are doing a triangle with legs A, B, and C, pretend this is a closed triangle, and the semi-perimeter would be half of that. This is Heron's formula, and it is a representation of the area of a triangle if you are given the sides. And that's a pretty basic formula, but it actually comes from another interpretation of the law of cosines, which in and of itself comes from another interpretation of the distance formula. But I'm getting ahead of myself. This is obviously a trigonometry like subject, but this is actually going to be more algebra focused than anything. But still, this pipeline is going to be distance formula to law of cosines, and then to Heron's formula. So yeah, it'll go from here to here, and then I'll actually talk about a determinant, a very special determinant that uses A, B, and C as inputs to depict Heron's formula in a more interesting way. But before we get to all that, let's talk about the distance formula. That is, the distance is the square root of x2 minus, not x squared, whoops, x2 is a coordinate, x2 minus x1 squared plus y2 minus y1 squared. These being points on a standard xy plane, like right there, and actually I'll keep it positive, we'll say, right there, and then right there. This is, x1, y1. I apologize for my handwriting. Must be late, but yeah, x1, y1, and then x2, y2. Already, you can maybe see the beginnings of a trig property that we can use, because with our points x1, y1, and x2, y2, if we were to draw a line connecting these 2 points, we'd also have to draw a line connecting these 2 points horizontally and vertically. And if you know, this is x1, y1, and this was x2, y2. I don't know why I keep writing squared. If this is x2, y2, then this distance right there, that would be x2 minus x1, right? And then this would be y2 minus y1, that like leg right there. And that's just because, we have, let me redraw this whole rectangle for the third time, because, did I say rectangle? No, triangle. So if this was x1 or x2, y2, and this was x1, y1, then that leg right there would be x2 minus x1, or like the general distance, horizontal distance between those 2 points. And then this leg would be the vertical distance. So with that, you might already be able to apply Pythagorean's theorem if we had that line, this being x2, y2, and then that one being x1, y1, then the distance, which we would write as d, using our Pythagorean theorem, we could write that as x2 minus x1, or the horizontal leg, that distance, squared, plus y2 minus y1, or the vertical leg, squared, is equal to d squared, or a squared plus b squared equals c squared, where a and b are legs, and then c is the hypotenuse. And for that triangle on our coordinate plane, d squared would be the hypotenuse. And so yeah, that's how the distance formula connects to the Pythagorean theorem. If we took the square root of both sides, then this just becomes that. But as for a proof of Pythagorean's theorem, I mean, that's more of like a you can do pretty much anything in math and find some proof for Pythagorean's theorem because it's one of the easiest proofs. Not easiest proofs, but like one of the easiest concepts to try and prove. One that I'm going to do today is just going to be, let's see which one I'm going to do. Okay, so we're going to have a rectangle, we're going to have a square, but we're going to make it out of right triangles with A and B and a hypotenuse of C. And we're going to multiply that by 4. Unfortunately, I don't know how to do that. But yeah, it'll be that, and then that, and then that, that, and then that. That's okay. But yeah, this would be C, that would be A, and still B. And so this would be A, this would be B, this would be A, this would be B, this would be A, and this would be B. If we're just reapplying our idea that B is the longer leg and A is the shorter leg, and so this assembly of 4 right rectangles that are all congruent, or they have the same angle measures and same like side lengths. That's what congruent means. So 4 congruent triangles, right triangles, and we like connected their vertices or their ends right there, then we can say that this like shape in the center, even though I didn't do a very good job of illustrating that, it is a square. I know this is the poorest square imaginable, but still, this is a square with a side length of C, and then we have, this larger square length of A plus B, right? And already you can kind of see it. But yes, if the area of this square, whoops, wrong thing. If the area of this square is C squared, then the area of these triangles, when added up, needs to equal that. So, actually, no, that's not how it's going to work. So, we're going to say that, let's find the area of one of these triangles that, like, assemble to make our larger square. So, we're going to have the area is of any of these, it would be 1/2 base times height, or AB, not H, AB. That's the area of one of these. And then the area of the larger square, this whole thing, that would be A plus B squared, because the area of any square is its side length squared. So with that, we would have A plus B squared, and then obviously our inner square, that would be C squared plus 4 times 1/2 AB. So we'd have C squared plus 4 times 1/2 AB, which would be A squared plus 2AB plus B squared is equal to C squared plus 2AB. You can, you can subtract 2AB from both sides, minus 2AB, minus 2AB, and then you get A squared plus B squared equals C squared. That is a very simple proof for the area of a right triangle. And I don't really know why I gave it to you. I suppose it connects back to how the distance formula is an example of Pythagorean's theorem and where Pythagorean's theorem comes from. So I suppose the original pipeline would actually be Pythagorean's to distance to law of cosines to Heron's formula to the determinant. But yeah, we understand what the distance formula is, so let's talk about the distance formula within the context of the law of cosines on some graph like this, we would have right there, we're going to have an obtuse triangle with endpoints 0, 0, or the origin, a 0, or some, length of a side, and then endpoint right here, that would be b cosine theta. Oh, actually, let me draw the triangle in the first place. So it would be out here, and then along the x-axis. And this endpoint right there would be, let me let me first define what points each point is. We'd have C, B, and then A, and the angle or the side opposite B would be lowercase b, the side opposite C would be lowercase c, and then the side opposite A would be lowercase a. So our endpoint for A would be B cosine, let me write it off here then, B cosine theta, B sine theta. That's just like, yeah, B cosine theta and B sine theta are just representations of values that would help us make a more general case for our law of cosines. We're going to use, some elementary algebra, and we'll have it. So our endpoint for A is equal to B cosine theta, and then B sine theta for the y coordinate, and then B is equal to the point at A, 0, and then C is the origin, or 0, 0. And now using the distance formula, which, as we established, is just an extension of Pythagorean's theorem, we'll have the square root of A minus B cosine theta squared plus 0 minus B sine theta squared. And this is just saying that the largest side of our triangle, which looked approximately like that, C, is equal to the distance between that point A and then that point B, which, is kind of easy to tell using common sense. But yes, we have this nice little representation of what C would be. And now if we were to expand this outwards, we would say that C squared is equal to A minus B cosine theta squared plus, I'm just going to, square the negative already, because 0 minus anything is just going to be that thing but negative, and any negative squared is just going to be like a positive number. So negative B sine theta squared is just going to be B sine theta squared. So with that, you can you can write that down, think about it, but we're just gonna expand this outward, and this is just algebra. We're not gonna worry too much about this, but if C squared is equal to A minus B cosine theta squared plus B sine theta squared, then, and we're not going to do anything with our cosine thetas or sine thetas, we're just going to leave them as is. That would be A squared minus 2AB cosine theta plus B squared cosine squared theta. I mean, because cosine or sine or anything squared is equal to cosine squared, that thing. It's just a different notation. But yeah, This is b squared cosine theta squared because while this is one number, we are squaring this and then squaring that, um, because uh, like cosine theta is technically a constant, even though these aren't variables that are defined yet. So with that, we'd have b squared sine theta squared, and then all of that can be simplified a little bit further. If we chose to factor out the b squared of, let me erase that. If we were to factor out the b squared right there and then the b squared out there, then we would have a squared plus the factoring out of the b squared sine squared theta plus cosine squared theta. And anybody who's done their trig identities is already a little bit excited because we can simplify that pretty quickly. But let me just put down our 2ab cosine, cosine theta. Now, sine squared theta plus cosine squared theta is equal to 1. That proof, I mean, I suppose I could show it to you. Let me find that real quick in my notes. This, like most of the stuff that we've been doing so far, is going to require Pythagorean's theorem. So, using a triangle with legs A, B, and C. This is meant to be a right triangle, even though it's not a 90-degree angle right there. This will be theta, and we'll say that sine theta is equal to A over C, or the side opposite the angle and the hypotenuse, so it would be A over C. And then cosine theta would be B over C, or the side adjacent to the angle over the hypotenuse, or the ratio between those sides. So with that, we have A over C and B over C, and then squaring them, that's just a pretty simple A squared, C squared, and then, C squared, and then B squared over C squared, which, it's pretty simplistic. And then with that, we can expand this a little bit further. Sine squared plus cosine squared, if our angle's theta, would be A squared over C squared plus B squared over C squared. And since they have a common denominator, we can join them in the numerator. And then, obviously, this looks pretty similar to our Pythagorean's theorem, which, need I remind you, is A squared plus B squared equals C squared. So, if we were to divide both sides by C squared, we would have A squared plus B squared over C squared is equal to 1, because C squared over C squared is equal to 1. So that's just a small little proof of why sine theta squared and cosine theta squared is 1. But yeah, this would be A squared plus B squared times 1, which is just going to be B squared, minus 2AB cosine theta. This is the law of cosines, and it can kind of tell you what almost every side is if you are given like theta in that like formula. But yeah, this is the law of cosines. And then with more algebra, we're going to expand this into Heron's formula, which is the intent of this video, what we've been trying and very slowly building up to. So using our law of cosines, which I'll just write once more, I'll actually write it in a slightly different way. We'll say that we have a triangle A, B, and C. Then opposite those sides, we have alpha, which is not whatever I just scribbled, It is the first level of the first letter of the Greek alphabet, and it is used often in trigonometry. But we'll have, that's an okay, alpha. And then we'll have beta, which looks like that, be the angle opposite our B, and then gamma, which, if memory serves, looks something like that. Yeah, that's an okay gamma. And that will be the angle opposite C. And then with that, using our law of cosines, we can write, well, actually, let me write down our law of cosines using our gamma notation now. It would be a squared plus b squared a squared plus b squared minus 2ab cosine gamma. I probably should have used gamma to make this transition slightly less odd, but you know, hindsight's 2020. So we have c squared equals a squared plus b squared minus 2ab cosine gamma, and if we were to try and isolate this cosine gamma, this is just going to be, you know, this is fully algebra. We're not doing any trigonometry right now. No evaluation of this cosine just yet. But if we were to isolate this cosine gamma, we would have to, you know, isolate this whole thing. So we would subtract a squared plus b squared, or I suppose we can bring this to that side and then bring this to this side. So our calculation gets a little less muddled. So with that, we would bring this to the left-hand side because, you know, there is a negative and we want to make that a positive. We'd have 2ab cosine gamma, like that, is equal to a squared plus b squared minus c squared if we were to subtract c squared from both sides. So now we can isolate our cosine gamma by dividing both sides by 2ab and 2ab, and so our final thing would be cosine gamma is equal to a squared plus b squared minus c squared all over 2ab. And using another trig identity, we can find the sine of some gamma. And the sine is usually showing the altitude of some triangle. Like using our trig identities, it's most often cosine shows like the adjacent side, and then sine shows the hypotenuse, or not the hypotenuse, it shows the side opposite the angle, and that tends to be the altitude, the height of an altitude that is dropped on any triangle. So finding sine would be pretty helpful if we were to use our generalized area equals 1/2 times base times height, or altitude. So sine would be a stand-in for our h. So sine gamma is equal to, I keep writing y's. I suppose that's just force of habit, but it'll be like that. Sine gamma is equal to sine squared, sine gamma squared is equal to sine squared gamma, which I'm just going to leave as a y right now. And sine squared gamma is equal to 1 minus cosine squared gamma. So with that, we can say that the square root of that and the square root of that would be sine gamma is equal to square root of 1 minus cosine squared gamma, which we can then plug in our original cosine gamma is equal to a squared plus b squared minus c squared over 2ab. We would be able to, write that in here. We can have the square root of 1 minus a squared plus b squared minus c squared over 2ab. And that would just be, 2 well, this would be squared, right? So we'd have, if we were to try and maybe leave some breathing room in the future to do like a difference of squares. If we were given a squared minus b squared, we can factor that to be, a plus b times a minus b, which would be much easier to work with in comparison to our somewhat temperamental like formula right there, which is pretty difficult to do anything with right now. So if we wanted to leave ourselves some room to do that, we'd be able to say that 2ab squared would be 4a squared minus b squared. Not minus b squared. It's going to be 4a squared b squared. And if we gave ourselves the room to do a difference of squares in the future, we would have 4a squared b squared over 2ab like whole squared, which if we were to do a square root of, we would be able to factor, or not really factor, but take out that 2ab and just leave that in the denominator. So we'd have 2ab, we'd have a squared plus b squared minus c squared squared, the square root of that, all over 2ab. And now, I know that this looks more complicated than this one. This is actually more easy to work with. So, given that, let's break this. Not break this, but let's try and make some type of use case of that relatively complex formula. So, if the area of a triangle is 1/2 base times height, then the altitude of the triangle on base A would be b sine gamma. If you think back to our original triangle that we drew, if sine gamma was to be the opposite of theta in some right triangle, then the altitude of the triangle on base A would be b sine gamma. So we have the area is equal to 1/2 base times height, or 1/2 ab sine gamma. That's a times b sine gamma, because if our base is a, then our height or altitude height would be b sine gamma. So we know that sine gamma, well, we know what it is now. So let's write that out. We have, well, let's actually do something real quick. We know that 2ab is already on the denominator of our original long thing. It was like all that, and then 2ab was on the bottom. So we see that ab is already out here, and we think, hey, maybe we can do something to eliminate the denominator in our first step. So 1/2 2ab is going to be regular ab, and 1/4 2ab is going to be 1/2 ab. So if we have 1/4 2ab, times all that stuff on the numerator over 2ab. We can cancel out our 2ab's, leaving us with just this 1/4 and just whatever was in that numerator. So I'm just going to skip that step and take out any ab's, at least the beginning, and we'd have 1/4 square root of 4a squared b squared minus a squared plus b squared minus c squared whole squared. And now we're going to do our difference of squares. That would be, I think I said a squared minus b squared is equal to a plus b times a minus b. So with that, we can just write that out. We'd have, if this was our a and this was our b, then this a would be 2ab, and then this b would be a squared plus b squared minus c squared. Because this whole thing is squared. It's not like a one thing. So let me get that out. Oops, not redo, undo. So we would have, if our difference of squares, that would be 2ab plus a squared plus b squared minus c squared times 2ab minus, let me keep it in parentheses now, a squared plus b squared minus c squared. And then we extend our square root sign. So just copy that down for a second. Okay. And I'm actually just going to rewrite that in a slightly different fashion so that you see what we can do. If you notice, we had a 2ab for both of our factors, and we also had an a squared and a b squared. With an a squared, a b squared, and a 2ab, you can do quite a few things, but right now we're going to do squares. So I'm going to rearrange our previous step. We would have, that was a weird square root sign. It would be, let me actually just try it like that. It would be a squared minus 2ab plus b squared plus c squared if we distributed that negative, and then a squared plus 2ab plus b squared minus c squared. And so already with that, we can do some more algebra. So we can say, hey, this is a squared minus 2ab plus b squared. That is our classic a minus b whole squared plus c squared. Oh, no. I did something wrong. Very wrong. Let me go back. We are left with, maybe I should have done this a little earlier in the day so I'm not as fried, but 1/4 square root 2ab, I'm just going to go back to our original first step, minus a squared plus b squared minus c squared, that's in parentheses, times 2ab plus a squared plus b squared minus c squared. So this one would be 2ab minus a squared minus b squared. We can factor out the negative, and then that would be minus a squared minus 2ab plus b squared, which is what we want. And then we would have a squared plus 2ab plus b squared minus c squared, which is what we want. And then this is going to be obviously a plus b squared. So with that, let me do the correct expansion. And then this next step would be 1/4 square root of c squared minus a minus b squared times a plus b squared minus c squared. And this is just going to use difference of squares again. We would have, let me write this all down. We would have 1/4 square root of c minus a minus b, c plus a minus b, and then a plus b minus c, and well, that was an unnecessary end parentheses, so it would be c right there, times a plus b plus c, and then that. And we're going to reincorporate our 1/4. We want everything to be in the middle of our square root. Or not in the middle, but like we want it to be inside the square root to ease in our calculations. So let me write all of this one more time. We would have c minus a plus b. I'm just gonna, distribute the negatives and then we'll rearrange in our next step. But we'll have c minus a plus b times c plus a minus b, and then a plus b minus c, and then a plus b plus c, all over 16 if we were to square everything. Because, if we have 1/4 squared, whatever's inside of a square root, we can reincorporate 1/4 because 1/4 is just obviously the square root of 1/16. So the square root of 1/16 times all of that is just going to be 1/4 square root of all that. So reincorporating that 1/4 under our square root allows us to section off. We have 4 terms, so we can break this 16 into 4 equal values. And what I would do, because I know that 2 to the power of 4 is equal to 16, I would split this 16 into c into these terms over 2, like that times that times that times that. And yeah, that should be a good way to represent this. So let's erase this once more, and let's rearrange our terms. This is more like, I suppose, to help you guys, but yeah, let's reintroduce our concept of the semi-perimeter. If you can remember from that far ago, it is the perimeter divided by 2, and the perimeter of any rectangle with sides A, B, and C is going to be A plus B plus C. So the semi-perimeter is that going to be A plus B plus C over 2, which, if you remember, is one of our terms in our expansion. So this is going to come out really nicely. Let me write it in a way that helps you understand that in a little better. We have A plus B plus C over 2, which, remember, is our semi-perimeter, times B plus C minus A over 2 times A plus C minus B over 2. This might seem like I'm randomly putting these together, but this is just a way to say, like, this negative is to the right so that we can make an easier looking subtraction, times a plus b minus c over 2. And if we have our semi-perimeter is equal to a plus b plus c over 2, then, this would be b plus c plus a over 2 minus 2a over 2, because we're trying to make a minus 2a so that we would have a negative instead of a positive at that point. So if we had, b plus c plus a minus 2a, then that would be s minus a if we canceled out our 2's. And that could be, reapplied to our other terms right there. So this comes back to our original Heron's formula. If this is S, then the area of any triangle would be, well, not any triangle. If the side length is 0, then that's like a special case. But, the area of any triangle with real numbers would be S times S minus A times S minus B times S minus C. And, yeah, that's just where we get our Heron's formula from, with a bunch of mini proofs around the way. I think this is a pretty interesting lesson because, it doesn't have to be taught like this. This could be taught in like 3 seconds, but I think this is just an interesting way to incorporate a bunch of proofs for concepts that might seem slightly, abstract. So, just some food for thought. We can write this in a slightly different way. This is, a little bit more advanced than I have taught, and does require understanding of determinants, which, if that does not ring a bell, then you should just click off this video already, because if I were to describe determinants and matrices and matrix operations, that would make me rant for at least another 2 to 3 hours. But, the Cayley-Menger determinant, I'm hoping that everybody who doesn't know what a determinant is has clicked off, because this is going to just sound very, very abstract and nonsensical. But the Cayley-Menger determinant is defined as the volume of some, like, dimensional object. Like, for any n-dimensional object where n is greater than 2, this would be, the volume, like, it would be the volume of a tetrahedron for n equals 3, but on a 2-dimensional plane, which is what we're concerned with, that would be n equals 2. This would be the area of a triangle. So the Cayley-Menger determinant, it's just basically a way of representing the volume of some n-dimensional object within k-dimensional space if k is greater than or equal to n. That's a disgustingly simple way of describing it, but I think that's a okay way to, very basically understand what it is. And the determinant simplified is v n squared is equal to negative 1 n plus 1 over n factorial squared times 2 to the power of n, and it would be 0 d01 squared. Like, I know anybody who knows what a determinant is knows that this isn't 1, this is just a different way of writing the like, position of some random number in our set. But, and then that would be d02 squared, and then this goes on until you get to d0n squared, and then it just ends at 1. Then you go to D0, 1 squared again. You might see a pattern. It's going to be like that. That's the general pattern of our thing. And then along this column, it would be D0, 2 squared. And then it goes down until you get to D0n squared again. And then the column ends at 1. And this just goes on. This would be 0, and then this would be D1, 2 squared, and then 0, and then this would be D1, 2 squared, and this goes on till you get to D1n squared, and then 1, and that like general pattern continues going on. Like this would be, D1, not 12, it would be D1n squared, and then that would be 1. And this just kind of goes on for the rest of your matrix until you find what n is. For us, it's going to be 2. So if we were to plug in our values, we would have, within the context of two-dimensional space or a triangle, that would be like if we were to write the area of a triangle and V2 is the area, then we'd have 16a squared. I could, evaluate all that, but this is just a little introduction to the Cayley-Menger determinant. We'd have 2a squared, a squared plus b squared minus c squared, and then a squared plus b squared minus c squared to b squared. And the determinant, which we all know is gonna be AD minus BC in a matrix that looks like, God, why can't I draw a straight line for the life of me? C, B, D. If we have that like matrix, then the determinant is going to be AD minus BC. So yeah, if we multiply these two together, 2a squared and 2b squared, we have 4a squared b squared minus a squared plus b squared minus c squared, which I think is pretty cool. Squared, obviously. So yeah, that's just a way that determinants connect to Heron's formula. That wasn't meant to be like an introduction to determinants, or even like that wasn't meant to be anything. That was just, food for thought. But yeah, I hope you learned something. If you did learn something, please comment down below. If you did not learn something, constructive criticism is always encouraged. And if you're not in the mood for constructive criticism or a comment, then, I don't know, you can do some bench dips. But since this video was significantly shorter than my other derivatives video, we're gonna have not a full album, but one song, and that is the recent single from one Isaiah Rashad, Headshots for the Locals. And this has some explicit language. I mean, Modal Soul by Nujabes also had explicit language, but I think this might be slightly stronger. But yeah, this has a very I hesitate using this because I don't typically speak like this in my normal life, but it has a nice vibe. This dreamy, almost lethargic instrumental of like soul and trap and this nice intersection lends really well with Isaiah's very exhausted delivery. And it's a pretty exciting single from him. I listened to his other track, Lay With Ya, which with, I think it was Duke Deuce. That was also a fine track. It was just a 3 6 Mafia, um, not lay with what, it was lay with yeah, and it was just a them, rapping over some 3 6 Mafia flip, which I mean, it's fine, but very overdone. I think this is more unique and more emblematic of his discography. But yeah, listen to it, if you are okay with explicit language, and tell me what you think about it in the comments down below. All right, bye.